Okay, in this problem we have this collar right here, which starts in this position. Let's call this position 1, and we release it, and it goes down to this position right here, which is, we'll call this position 2. And we're going to say that the distance between position 1 and 2 is equal to 1 meter. And the thing about this collar is it's attached to this spring. And when the spring is in position 1, this distance from right here to right here, the length of the spring is equal to 0.75 meters. And we're told that the spring at this point is unstretched. So when a spring is unstretched, that means it has zero potential energy. Now, at this point too, the spring might be stretched a little bit more. We're going to have to look at the problem in a little bit more detail to figure out if there's potential energy from the spring at this point. But if it's released at rest, we want to determine its velocity at point 2. So what's the velocity of this collar at point 2? And we're releasing it from rest. So if we look at a quick free body diagram, we notice that the only force on this, it has a weight that comes down, and it's going to have this spring energy, this force of a spring. So it has a weight and a spring, and both of these are conservative forces, so we can use the conservation of energy. And the conservation of energy says the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And we can simplify this equation a little bit more because we said it starts from rest. So if we know our kinetic energy is equal to 1/2 times mass times velocity squared, we start from rest, so our velocity is 0. So our initial kinetic energy is equal to 0. Now our potential energy for gravitation is going to depend on where we put our datum line. And for this problem, I'm going to choose to put my datum line right through this first point. So what does this say? This says that I have no gravitational potential energy because my collar is through my datum point. And remember, my datum point is a line of zero gravitational potential energy. Anything above my datum point has a positive potential energy, and everything below my datum point has a negative potential gravitational energy. Now, there's two types of potential energies we have to look at. We have to look at the gravitational potential energy, and we have to look at spring potential energy. But the cool thing about putting our datum point here is our spring potential energy, because our spring is unstretched at this point, at 0.75 meters, our spring is unstretched. So we have no spring potential energy. So for us, our initial potential energy is also going to be 0. So now we just need to figure out our final kinetic energy and our final potential energy. Okay, so our final kinetic energy is just equal to this 1/2 times our mass, and our mass of this is going to be equal to let's say 2 kilograms. So 1/2 times 2 times a velocity squared. We don't know what this is, we're solving for our velocity, plus our gravitational energies. So our gravitational our potential energy is equal to our potential gravitational energy plus our potential spring energy. And potential gravitational energy is equal to m mass times gravity times a height. And let's just do this first. So this is equal to our mass, which is 2, times gravity, which is 9.81, times a height. Well, it's moved 1 meter, so it's 1 meter down. And we can't forget that this is a negative gravitational potential energy because it's below our datum line. So this is our gravitational potential energy. And if we look at our spring energy is going to be equal to 1/2 k times s squared. And this s right here is equal to the length that the spring is stretched. So we can figure out this length right here. We go 1 meter down, 0.75 meters across right here. So this is a triangle, and this triangle is a right triangle. So we know that this is 1 and this is 0.75. So this length is going to be the square root of 1 squared plus 0.75 squared. And this is going to equal to 1.25 meters. But this is asking for the length that the spring is stretched. We know the spring is unstretched at 0.75 meters. So this is going to be equal to 1/2 times the spring constant, which is 3, times this 1.25 minus the amount that the spring is initially with it not being stretched. So that's 0.75 squared. So this is going to be equal to 1/2 times 3 times 0.5 squared. And so we can put our let's rewrite this over here. Let's rewrite this to 0 is equal to 1/2 times 2 times velocity squared minus 2 times 9.81 times 1 plus 1/2 times 3 times 0.5 squared. And if you notice, this equation only has a velocity term. So we can solve for this velocity, and we get the velocity at this point. So the velocity of 2 is equal to 4.39 meters per second, and the velocity is moving downward.